And we'll move now to the second presentation by Mike Paquette, who's going to talk about load testing high-capacity caissons in Manhattan. Mike, the floor is yours.
All right, thanks, Gerald, and thanks, Seth, for an interesting presentation. Let me see if I can, here we go. I'm going to segue into another very large project, the famous or infamous Hudson Yards, depending on who you ask. And I think that you're going to hear a lot of very similar themes here in this quick talk about how advanced load testing done pre-production and really pushing the limits of what the rock in Manhattan can do totally transformed the way this project was done and had a very significant impact on the project schedule. So just to set the stage, hopefully a lot of people have heard of Hudson Yards. It's on the west side of Midtown Manhattan. And if we kind of zoom in, you can see this round structure on the right-hand side is the Madison Square Garden, just to locate where we are in Penn Station. So the two sites highlighted here on the left comprise Hudson Yards, the East Rail Yard, and the West Rail Yard. So you can see this occupies about 6 full city blocks in downtown or in Midtown Manhattan in a very populated area. This is what the yards look like pre-production. Again, you can see up on the left corner photo here, this is a lot of real estate in the middle of Manhattan. So prime development opportunity, and one of the biggest and most expensive construction projects in U.S. history. This is what the current situation looks like. So it's a bit different from what you saw in the previous picture. You could see that the East Rail Yards are gone now and covered over by a platform. The rail is actually underneath that, and you've got 4 towers on top of that, and there's some additional towers north over here that are currently under construction. Right now, a total of 5 towers have been completed out there. Little site history. This is a map from 1836. It's basically oriented with north to the right here. So the West Rail Yards, this purple line that I've drawn onto the map is actually 11th Avenue that splits the yards into the East Yards and the West Yards, as you saw in the photograph. So you can basically see that the West Yards is entirely outboard of the old historic shoreline in Manhattan, and the East Yards, the historic shoreline, actually splits through part of that. So pretty important in how the foundation design for the project evolved. Everybody likes a good subsurface profile shot, right? So this is the East Rail Yards. The big takeaway here is that rock is, in terms of Manhattan, relatively shallow in the East Yards, 20 to 40 feet deep. We've got a lot of historical fill here, overlying, medium dense sands, silty sands, and a little bit of organic river deposits in that area that I had highlighted on the old map that was outboard of the shoreline. The West Yards, on the other hand, you very quickly, as you cross over 11th Avenue, the bedrock just drops off. And by the time you get out to about 12th Avenue on the far west, rock is over 130, 140 feet deep over here. And the material above it is all river mud with fill. So this is weight of hammer, 1-2 type blow count or organic silts and clays. Some photos of the type of rock we're dealing with out here in Manhattan. The north side of the site, is actually very good, high quality, high strength, hard rock. You can see it's primarily mica schist, but you can see some inclusions of granite and pegmatite into the mass here. The south side of the site, however, you can see this darker band here in the center of the core run is much poor quality rock, much weaker. This type of thing you hit with a geology pick and it'll kind of crumble apart, much lower strength. So we're dealing with 2 very distinctly different materials at the site. As I said, so how do you build 5 towers on top of an active rail yard in the middle of Manhattan. And the key to that is basically to put a platform over the rail yard and then build your towers on top of that platform. So what's being kind of shown here in this gap between the platform and subgrade, these small dots that are shown here, all the active rail tracks. So every 3 to 4 sets of tracks, there's a column that comes down between the tracks, and then a caisson that gets drilled down to bedrock. To complicate things, we also have the existing Amtrak tunnels from New Jersey coming directly under the site, and a new Amtrak tunnel that was constructed while Hudson Yards was being constructed. Amtrak knew that this was going to kind of shut off their chance to ever put a new tunnel through here, so they preemptively put a box tunnel sitting under the yards that they will hopefully connect to someday. So brief history of caisson design in New York City and how we ended up getting to the point where we did a pretty robust load testing program on this was in New York City, caisson design is kind of code dictated. So in the 1968 building code, there was a presumptive skin friction value for rock sockets of 200 psi. In 2008, this value was omitted, and then back into the 2014 code, the 200 psi found its way back in. So pretty much every tower in New York City is based on this 200 psi value, and we've got 50 years from 1970 of a long track history of that performing well. As far as end bearing on the rock goes, it ranges from 40 to 120 kips per square foot, depending on the quality of the rock. So in New York City, class 1C rock is kind of a poor quality, weaker rock. Class 1A is that very good, high quality granite. You're talking RQDs of greater than 90 and high compressive strengths. So there's a bit of a history behind these values. I was a little curious, where did that 200 psi actually come from? Turns out it was based on one test back in 1936 by the Western Concrete Pile Corporation. They put in a caisson, which was a new technology at the time, on 56th Street, a drilled caisson that is, 56th and 12th. It was a 12-inch diameter, what we would call a micropile today. They did a tension test. They proved out, almost 400 psi of skin friction and didn't have any signs of failure whatsoever in that test. So basically petitioned the building department for this new pile type. The 200 psi applies a factor of safety on that. And then the first job that was really full production of caissons in New York City was in the Brooklyn Navy Yard, where about 180 of these caissons were put in using the 200 psi. So the big question on Hudson Yards was, do we load test or do we just stick with the 200 psi? That's tried and true, long history of it, and we know it's going to work in New York City. And really what it came down to is this, that in order to build these towers over the active rail yard with the trains running 24/7 while this is being built, we needed to put in over 700 caissons. That's split between the 2 yards. So in the east yards, which is the part that's actually built right now, there's about 380 caissons. These are typically 3 to 6 foot diameter. Capacities range from about 20,000 to 51,000 kips. That's not a typo, that is 51,000 kips. Rock sockets anywhere from 6 to 52 feet long. And really, on average, we were getting production rates of about 1 hour per foot when actually down on the rock socket and hammering away at the rock. So if you just do a little bit of quick math and you say we got 700 caissons and the average rock socket is ballpark 30 feet, maybe it's 25 feet, 30 feet, that's 21,000 hours of just sitting there with a drill rig hammering on the rock, not even accounting for the time to sink the casing to the rock, the time to move the rigs around, all the time to pour the concrete, the logistics of the rail yard, etc. You back that out, it turns out to be 875 24-hour days nonstop of hammering on rock, which is the equivalent of a single rig sitting there for 2.4 years just hammering rock. So this is the conditions that the contractors were dealing with. On the left-hand photo, you can see the yards are very congested in the east yard, kind of next down before it heads into Penn Station. They could give us a couple of tracks, usually 3 to 4 tracks were outed at a time, but the rest of the tracks would remain in service while this was being constructed. On the left-hand side of the photo, there's a cut and cover tunnel being constructed. That's the new Amtrak tunnel. The logistics of actually drilling caissons in the middle of a rail yard are just incredibly complicated. And I can remember, being out on this site and looking around, and at any given time on a single drill rig, you would probably have 20 to 25 people dedicated to dealing with, how do you get the spoils out? How do you get the spoils out of the yard? There's a crane lifting supplies over the track. There's railroad flagmen, there's the engineer, there's the safety people. It's a massive undertaking. And everybody knew this going in. So the real question was, is there anything we could do to shorten these rock sockets and basically get off these rail tracks as soon as possible? Because as soon as the platform is over the rail yards, constructing of the towers can kind of proceed without impacts on Long Island Railroad or commuters or anything like that. So the key to this job in Hudson Yards, as with most jobs, your biggest risk was the subsurface. That, like I said, the big question was, can we prove out a higher skin friction to basically get everyone off the tracks? You can see lower right photo here. There was a period of time where there were 4 bower rigs out there, 2 cranes servicing them. Just everything they could do to get these caissons in the ground as fast as possible so that they could stop impacting the railroad. So not very often that you have a mega project like this, and I think it was a pretty unique case to really see how advanced load testing can shape a large project. We actually had 9 bidirectional load cells load tests. These were these were done throughout the course of the project, but primarily started ahead of production caissons in the east rail yards. So in the east rail yards, there were a total of 4 tests. In the west rail yards, where the rock is very deep, there were another 3 tests performed. There was a test performed north of Hudson Yards for another project that's Hudson Yards related, but it's actually outside the tracks. Then we were actually able to obtain this number 6 at the top of the page, the load test data from the Jacob Javits Center. So combined, we had a total of 9 tests here, which I think is a really unique opportunity that you don't often see. This is why the question really came up: Are we going to load test or not? I got the figure from the construction manager, Tudor Perini, on how much it costs to do those 2 load tests within the north part of the rail yard. It's almost $600,000. So this is a big chunk of change for the developer to swallow. But when you go back and you compare this to the cost of 20 people sitting on a rig times 4 rigs times 18 months on site, it quickly became apparent that everybody wanted to proceed with doing the load tests. We had a couple of different situations for load testing out there, and I'll describe quickly here how we ended up with these. The first couple of tests as shown on the right were full caissons drilled down to rock and then fully grouted all the way back up. The 55 Hudson Yards, which is that site that is just north of the yards, we actually had rock at the ground surface, so the sockets were basically just constructed directly into rock. And then based on the early results of the first set of load tests, subsequent load tests were actually constructed where the only part of the element that was grouted was deep down in the rock, and we'll talk quickly about that in the next couple of slides. So getting into the actual results of the load test, this is a plot of the 9 tests together. Y-axis is mobilized unit skin friction versus x-axis is displacement. So you can kind of see that there's 2 groups of data here. I'll talk about why. And then I've got the New York City Building Code 200 PSI value plotted down on the bottom. You can see every single test achieved that and some significantly more. As far as end bearing goes, plot y-axis here is unit end bearing versus displacement. Again, I've got the 9 tests plotted and the 3 New York City building code based on rock quality. And you can see most of these tests clearly surpass those in end bearing. Tests 7 and 8 were, we think what happened in 7 and 8 is if you actually look at how these performed when they got out to larger deflections, we think they basically had, both of these tests were in the west yards where rock was very deep. And we think that the bottom of the sockets potentially were not cleaned out sufficiently, and that the initial part of this curve was related to basically compressing sediment on the bottom. And then once the rock got engaged, it basically has a similar trend and result as all the other tests. So where did we end up based on that? In the east rail yard, everybody agreed to push the north side where we had good quality rock up to 300. The south side, where we had some poor quality rock based on borings, kept it at 200. End bearing, certainly able to justify an increase in end bearing. And then on the west rail yards where rock was very deep, we held the end bearing back because of that known problem, and actually suggested giving the contractor an option during construction to just ignore end bearing and increase the socket lengths to be entirely for skin friction, which usually only ended up being about 1 diameter. So one of the things that we encountered in the load tests and why we kept the tension design so low is that those tests that came back with the much lower skin friction values, we think based on discussions with Fugaro load test who did these tests, that one of those, at least one of those, and possibly 2 of them, what might have actually happened was not a skin friction failure, but we may have actually pushed the socket and fractured the rock and basically failed the rock mass. So instead of proving out an actual ultimate skin friction, we think we failed the rock mass. And back to that slide that I showed earlier, why the subsequent later load tests were adjusted and they were all deepened and dropped deeper into the rock. The goal of the load test is not to test the rock mass, but it's to test the bond between the concrete and the rock. So some quick conclusions on what we got out of these load tests. The first thing is that the rock quality was extremely important. So these lower ones, number 1, number 2, these are on the south side of the site where we knew we had that kind of poor quality rock, and you can very clearly see there's a much bigger difference between the poor quality rock getting between 200 and 400 ultimate skin friction, and the much higher quality rock getting in some cases close to over 800 or 1,000 psi. In addition to advanced load testing, I think this just speaks to how important subsurface exploration is to the design program. Second conclusion was that rock type was very important. Again, the granites were performing at a much higher capacity than the schists, which is reflected in the graphs below. And again, that goes back into the discussion of having a really high quality subsurface exploration program, especially if you're trying to push the limits of what can be done. Number 3, I brought this up at previous conferences when we've talked about Hudson Yards, and I always get an eyebrow raise on this as to whether it's really a thing or not. The test caissons were drilled with 2 different methods. Most of them were drilled with a down the hole hammer, but the ones that were in the soft, poor quality rock were actually drilled with a rock auger. And when you looked at the video camera inspections of these, you could tell that the auger kind of provided a much smoother, polished surface to the sockets compared to the hammer. Does the drilling method actually impact this? I think this is one where it's a question of, was it lower values in the skin friction because the rock was poorer quality or because of the drilling method? Kind of speculation here. They kind of go hand in hand, and causation is not, correlation here is not necessarily causation. So is the 200 psi a good presumptive value? I think if you're just doing a normal project, you don't have a lot of load test data, you don't have a ton of subsurface information data in New York City. I think the 200 psi code value is probably pretty good for what it is. It kind of represents the lower bound poor quality rock that we tested at the site. Are the end bearing values good? I think that they're based on what we saw out there. They're very conservative. We were getting significantly higher end bearing values than what the code allows. When you kind of look at these two graphs together, I think it's important that you have to keep strain compatibility in mind. And even though we as engineers like to think that we're getting a combination of end bearing and skid friction, when we look at these graphs, I think what we're really seeing, especially when we're when we have these caissons seated into very hard rock, is that we're mobilizing very high skin frictions and very low end bearings. So on paper, we're designing to lower skin friction and higher end bearing, but in reality, we're actually getting much higher skin frictions, and a significantly less proportion of that is going into end bearing. Recommendation to anybody that is considering doing a load test program like this is to avoid the problem that we had and potentially getting some artificially low results in testing high quality, high strength rock like New York City rock, is to deepen the bond zones. In some of these tests, the bond zones were put 10 to 15 feet below the surface of the rock, just to make sure that we didn't bust out or fail these in rock mass failure. And really, I guess these are all the conclusions put together, but the main thing here was that, by justifying a 300 psi skid friction instead of the standard New York City 200 psi skid friction, and you multiply that by 700 caissons, we were able to significantly shorten the construction schedule on this project, which has huge, obviously huge money implications, huge timing implications for getting the project on board. It was just overall a massive, I think, win and success, just to show how valuable load testing can really be to change the course of a project. Yeah, so the East Rail Yard, which is the portion that's constructed now, 370 caissons. Those went in from March 2014 to November in 2015, so it took about 21 months to get 370 caissons on the ground. I think if we had gone with 200 psi, that schedule certainly would have been quite a bit longer.